So in the previous videos, we said that good machine learning algorithms have parameters that minimizes the algorithm's error or cost function. But how do we exactly find these parameters, these values of W and B, that minimize these cost function? Well, it turns out there's an algorithm that does this process for us, and it's called gradient descent, one of my favorite algorithms. And gradient descent is used to find the values of parameters W and B to minimize the cost function. So we have some function, right? JWB, this is our cost function, right? And we want to minimize JWB, and we want to find the values of W and B that do so. And this cost function, J of W and B, works for any model, so not just linear regression, but also other functions. So we can generalize this to say we want to minimize the cost function with a bunch of parameters, right? W1, W2, and we want to find these parameters that do this first, okay? So let's go over the outline of what gradient descent looks like. So in gradient descent, we'll start off with some W and B. Say we'll set W equal to 0 and B equal to 0, okay? We have to initialize our parameters to some values. And what we'll be doing with these parameters is that we'll be changing them to reduce the cost function, JWB. So we're going to change WB to reduce our cost function. And we're going to keep doing this, iteratively doing this, until we find a minimum. So say we have our cost function, and it looks something like this. Well, we want to reach a minimum of the cost function because we want to minimize the error of our machine learning algorithm. So we'll try to find the minimum. Right, gradient descent will find the values of our parameters to minimize our cost function. And this is the minimum right here. But it's also important to note that for some functions, such as this one that I graphed right here, there's more than one minimum. This point is minimum, and this point is also a minimum. So gradient descent may not always find the absolute minimum, which is this point right here, but it may also find a local minimum, such as these points. Okay, but in reality, our cost function is not always a squared error cost function, or as I like to say, a two-dimensional graph. For example, here we have another cost function, but this is three-dimensional. We can see that here on this axis, we have our values of W, and on this axis, we have our values of B, and here on this axis, we have our value of J, so our error or our cost. So you can see that here, this was two-dimensional, right? But this is three-dimensional because we have two parameters instead of just one. What gradient descent does is iteratively determines how you should change the parameter values to minimize J. So say we initially started here. What gradient descent is going to do is basically guide us to a minimum. So it might say, hey, the steepest step we can take to get to a minimum may be in this direction. And then it might be in this direction. And then this direction. Here, 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 and then here, until we finally reach a minimum. So gradient descent will basically help us change our values of W and B to minimize our value of J, our cost. And depending on your starting point, you may end up at a new minimum. So if we started somewhere here, maybe gradient descent might have told us to go this way until we reach a minimum over here. And like I said, even if our cost function has multiple minimums, that doesn't mean that we'll only reach one minimum here, right? We can also reach a minimum here. So it also depends on where we start. That affects our ending point, which minimum we get to. Okay, so what does the gradient descent algorithm exactly look like? I'll abbreviate gradient descent to GD for now. So we're going to be changing our values of W and B, but how does this mathematically look? So W is going to be equal to its value, W, minus alpha. And we also call this the learning rate, multiplied by the derivative with respect to W of our cost function. Okay, and yes, this has some calculus to it, but don't worry, even if you don't understand calculus, I'll explain this process to you. Okay, so alpha is our learning rate, and it's generally a small positive number between 0 and 1. And alpha, our learning rate, controls how big of a step we take downhill, okay? And then our derivative term, so here it was the derivative with respect to W of our cost function is just a derivative of the cost function. And this derivative tells us in which direction we should go. And we'll be repeating these steps until we reach convergence. And I'll explain to you what convergence is a little later. But it's also important to note that we'll be changing our parameter B2. Because in our three-dimensional cost function here, we have two parameters, W and B. So for as many parameters we have, we'll have to change all of them iteratively using gradient descent. So B will change by this, B minus alpha, it's the same learning rate used previously, but instead we'll be taking the derivative with respect to B of our cost function. Okay, and like I said, we'll be repeating these steps until convergence. Convergence means when we reach the point at the local minimum of j, our cost function, where w and b no longer change much with each additional step we take. So basically, it means we'll repeat this algorithm to change our parameters w and b until we reach our minimum. It's also important to note that we must simultaneously update our values of w and b. So this is how it will look in pseudocode. We're going to store these new values of w and b in a variable called temp w. So same formula we just learned above. And we'll do the same thing for b, okay? And then we'll assign our value of w to temp w and our value b to temp b. And we had to do this instead of just doing this, right? If we hadn't done this and we said, hey, w is equal to this thing right here. When we calculate our new value of b here, then we're going to be using our updated value of w right here. And we don't want to do that, right? We want to use our previous value of w because the values depend on each other. And then we'll initialize these values of w and b to the new values, which we just stored in temp w and temp b. So I want to visualize what gradient descent exactly does. So let's say we only have one parameter for our cost function, okay? So instead of j of wb, it's just gonna be j of w. So this will prevent us from using this type of a three-dimensional graph for now, and we'll just be looking at a two-dimensional graph. So we have our graph of our cost function. Looks something like this. On the x-axis, we'll have our values of w. The y-axis, we'll have our cost. And of course, it's gonna look something like this, right? We have a minimum here. So say we start with a value of w that's over here, because we initialize values of w and b to the values, and then we use gradient descent to change these parameters. So that way we can reach the minimum of our cost function. So say we start w right there. Okay, well, we're going to use gradient descent to reach the minimum. So what this term is, right over here, is a derivative, or the instantaneous slope of our cost function. So if we were to draw the slope at this point right here, it looks something like that. Our slope is positive here. So when we change our value of w, we're going to have w is equal to w minus alpha, our learning rate, and our derivative is going to be multiplied by a positive number. And what this does is decreases w. This term is going to be subtracted from w, decreasing w. So we're going to move w this way and get closer to our minimum. So eventually we'll get to this point over here. Now let's say we start with a different value of w. Say this time we start with the value of w over here. So this value of w is under what the optimal value of w is to find the minimum of our cost function. Okay, so our slope is negative. Our derivative is less than 0. So what will this mean? If we use our formula again, w is equal to w minus alpha times the derivative with respect to of our cost function. So this term now is negative, right? So w is equal to w minus our learning rate times a negative number. Well, if you look right here, there's a negative here too. So then this entire thing right here is going to end up being a positive number. So we're going to end up adding something to w. What that means is our value of w will shift this way. Now, this value of w is getting closer to that optimal value of w to minimize our cost function. So look at that. Gradient descent, this algorithm that we learned right here, is basically changing our parameters to minimize our cost function. Super cool. But how do we choose a good value of alpha, our learning rate? Well, this is the formula, okay? If our learning rate alpha is too small, we're going to end up taking baby steps. Let me show you what I mean. So we have our cost function here. Maybe the next point, gradient descent will tell us we'll change w to b is right here. Right, we'll change a little more. But our steps are going to be very small, okay, until we eventually get to our minimum. And the reason why this is true is if alpha is small, then technically this entire term is going to be small, right? If you 0.0001 times any value, right? This value is going to be something small, okay? And if you subtract or add a very small value, w is basically going to remain the same. So gradient descent will still work in this situation, but it may be slow. Now, looking at the opposite, when alpha is too large, we're going to end up overshooting the minimum. Say we start right here, okay? When we use gradient descent, we're still going to be traveling in the right direction. But if we choose too large of a value of alpha, w is going to change by too much. So now it might end up over here, right? And it's going to do the same thing. Now it's going to go the other way, and it's going to keep overshooting. So instead of converging to the minimum down here, it's actually going to diverge and get even farther from the value of w that we're seeking. So it's very important to find the right value of alpha, because too small of a value of alpha will result in the gradient descent taking a very long time, and too large of a value of alpha means that we won't even find that optimal value of our parameter. I also would like you to note that once we find a minimum our parameters won't change anymore, meaning gradient descent is done. Then we find a minimum right here. This is our cost function, just to specify. This derivative is equal to 0. It's flat. The derivative of the instantaneous slope here is equal to 0. And when we look at our formula, we have w is equal to w minus alpha times the derivative. When this is equal to 0, our value of w won't change anymore. Last thing I'd like to go over is the fact that our steps actually become smaller as we get closer to our minimum. Not because the alpha or our learning rate is changing, it's just how gradient descent works. The reason for this is because our derivative term actually decreases. Yes, our derivative is still positive here, meaning that our value of w is going to decrease, but because the slope becomes flatter over time, if we look at the formula one last time, when our derivative is larger, our value of w is going to change to a greater extent. If our derivative is smaller, then w will not change as much. So we can see that using gradient descent will eventually get to our minimum, and we'll take initially larger steps and then smaller steps as we get to that optimal value. Okay, that's everything I wanted to go over in this video. I hope you found it interesting. Thank you.